We're 11.6b and we're going to graph polynomial functions of higher degree. We have 13 previous videos and they're linked in this description if you get lost or confused. Now we talked about in 11.6a how graphs of first degree polynomial functions are lines and graphs of second degree polynomial functions, the quadratic ones, are parabolas. And synthetic division, the roots theorem, and Descartes' rule of signs are going to help us graph polynomials of higher degree with real coefficients. So there are third degree or cubic polynomial functions, and the graphs have two curves and may have an S shape or flatten out in the middle. We talked about this in the previous video, and also that there's fourth degree or quartic polynomial functions, and they might have a W or M shape depending on if they open upwards or downwards, but these may also flatten out in the middle. Now, we got 5 rules here to help us graph polynomials. The first thing we do is look at the degree of the polynomial and its leading coefficient. That's going to give us a lot of information about the general shape of our graph. We look for symmetries. When symmetrical points occur, the rest of the graph can be plotted quickly. There's going to be links to videos 9.1a, b, and c where we talked about symmetry in this description. You can link to it. We make a table of values for x and f of x, or you could say it's p of x or y. It's all the same thing. It's basically x and y. We use synthetic division. And we find the y-intercept and as many x-intercepts as possible. The x-intercepts are roots of the polynomial. And remember the theorems about the roots and Descartes' rule of signs. We plot the points, then connect them appropriately. So we can graph this polynomial, p of x equals 2x to the third minus x plus 2. And this is a polynomial of degree 3, because we have a little 3 exponent here. And the leading coefficient is positive, that's a positive 2. And the curve is going to have a general shape of a graph of a cubic function, because it's got a little exponent 3. And the function isn't odd or even, but 2x to the third minus x is an odd function with the origin as a point of symmetry. And p of x is a translation of this upward 2 units. This means the point x is 0, y is 2 is a point of symmetry. We make a table of values. So our polynomial is p of x equals 2x to the third minus x plus 2. Now, if we use synthetic division to make our table of values, the divisor will be x and the remainder will be p of x. All right? So I'll show you in a second. We have these as our x and y values that fit into this, and what I did was my synthetic division, so here's 1, and because there is no x squared, I had to put a 0 as a placeholder there. So we have a 2, a 0, a negative 1, and a 2 for our synthetic division. We drop down the 2. 1 times 2 is 2. We add them, we get a 2. 1 times 2 is 2. We add them and we get a 1. 1 times 1 is 1. We add them and get a 3. So we know that if x is 1, y is 3, or p of x. Same thing, okay? And we can do this table of values. And Descartes' rule of sign tells us there's either 2 or 0 positive roots because there's 2 variations of sign. We started with a positive. It went negative, so that was one variation. Then it went back to positive. That's the second variation. So because it's either a 2 or subtracting a multiple of 2, it's either a 2 or a 0. Those were the previous videos also. There's links in this description. And we can find out the negative roots, and we set these as the inverse of x for each one, and then we count the variations. So if we do this to the third power and it's a negative, that's going to make that coefficient a negative. So we went from a negative to a negative. Well, that's no variation. That stayed the same, to a positive. So we had one variation. So there's one negative root. And we plot this information and consider there's 3 possibilities. We either have 1 negative root, or 1 negative and 2 positive, or 1 negative and 1 positive of a multiplicity of 2. That means they're the same, okay? So we end up with this one. Actually, We don't know the shape of the curve between -1 and 1. So in between -1 and this 1, we're kind of lost about the exact precise shape of the curve. And this 0, 2, and between 0, 2 and 1, 3. So that means we need to plot more points between -1 and 1. So we come up with amounts that are between -1 and 1. And I came up with like a 0.85, and I came up with a 0.75, 0.5, 0.2, and then I did them in the negatives. And I used the synthetic division to make this table of values, and the divisor was x and the remainder was p of x, or f of x, or y, okay? And when I did 0.85, I got a remainder of 2.37825. So I just rounded it to 2.378. I could have rounded it to 2.4, couldn't I have? So after we find the points using a calculator, we draw the complete graph. So I came up with this, which closely resembled this, but this little yellow area is where I went into detail with the calculator and found more values for x and y. And I ended up getting this very detailed shape. So this is the yellow part expanded a lot, because that's a 1, that's a -1, and that's a 1. Where in this case, they're really tiny here, see? That's the -1, and that's the 1. So I blew it up really big by expanding the graph and came up with this shape, okay? So that's how to graph polynomial functions. It's really important you watch the previous videos, at least the last few, all right? Because that's going to help you a lot. You need to know about the root theorems, all right? Our next video is 11.6c, and we're going to continue talking about polynomial equations, and we're going to graph to approximate our solutions. And there'll be links to those 13 previous videos and those ones for Chapter 9 about symmetry. And I'll add this to the Algebra 2 playlist. This is the entire board. I'll back up for you so you can see what we did. And if you're lost about the synthetic division, this entire chapter of 11, all these previous videos, really explained in detail how to do it, okay? Just look at the links in the description. I'm really proud of you for watching math videos on YouTube. I want you to keep trying and just take baby steps, and you'll be amazed how far you can go, all right? Bye.